In this lecture, we are going to extend what we've learned up to now to fully 3 dimensions. You'll notice that there's really nothing new in this lecture. All of the concepts you need to understand a fully 3-dimensional finite difference time domain code is in the 2-dimensional finite difference time domain code and even the 1-dimensional finite difference time domain code. So we will be able to move fairly quickly through this lecture, but we will point out a few important things that you need to catch. So we'll start off by discussing the common grid strategies. This is an extension of what we learned, how we put PMLs, our record planes, our total field scatter field interface, our device, spacer regions, but extending that to 3 dimensions. No surprises there. Then what we want to do is set ourselves up for modeling something, a cross-grading, that's periodic, infinitely periodic in the x and y directions, but finite in the z direction. So we'll only have PMLs at the z-axis boundaries. In a way earlier lecture, we've already derived fully 3-dimensional update equations with PMLs everywhere. So in this lecture, we'll simplify those down to just having PMLs at the z-axis boundaries and periodic boundary conditions at the x and y-axis boundaries. And so we'll discuss how to do that. Then we need to extend our total field scatter field method of incorporating a source into 3 dimensions. And there's just more terms here, but all the concepts are the same. Then we'll generalize how we calculate transmittance and reflectance. Now that we go into 3 dimensions, we have more directions that our spatial harmonics or diffraction orders can diffract into. Then very last, I'll show you the MATLAB slice command, which is probably the simplest way for visualizing fields in 3 dimensions. So if we're modeling something that is not of infinite extent in 1 dimension or infinitely periodic, we need to put PMLs around all of the boundaries. So it looks kind of like this. And clearly inside this shell would be our total field scatter field interface, and then inside that would be some kind of device that's about a wavelength away from the boundaries. So that's how we do our finite size devices. In this lecture, we'll build up on our next grid scheme, and that's modeling things that are infinitely periodic in the x and y directions. So here's how we do this for 3 dimensions. Just like before, we will have PMLs at the top and the bottom to absorb outgoing waves. We'll have some plane near the top where we're recording reflected fields, some plane near the bottom where we're recording transmitted fields. We have our 2 slices that's at our total field scatter field interface, our device somewhere in the middle, and then of course our spacer regions, so that evanescent fields associated with this device don't touch the PMLs. So when we build a model like this, really what we're modeling is something like this. But since we have an infinitely periodic model, we really can't account for diffraction near the edges, so we're looking at the response throughout the bulk of the middle of this thing. And we've seen pictures very much like this for 2 dimensions. So nothing's changed here, just more dimensions. The next thing we'll do is we'll take our fully 3-dimensional update equations with PMLs everywhere and erase the PMLs on the x and y axes. So why even bother doing this? As we go up in dimensions or up in problem size, little tiny things that we think may not be such a big deal become a big deal and really hurt our performance. So it's always good practice when we're going large, and 3D is definitely large, to simplify our equations as much as possible. So the big thing here is erasing the PMLs at the x and y boundaries. And what we'll see is that our update equations simplify, and there's a lot of integration terms that we will no longer need, and we definitely here we want to split them so we have PML terms just associated with the top and the bottom. Before we're integrating these PML terms everywhere, we pointed out this is inefficient, but not such a big deal for 2 dimensions. But when we move into 3 dimensions, that is a big deal. So we need separate integration terms now for each PML region. So we start off, this is the full set of update equations for the HX field. But since we're getting rid of the X and Y PMLs, anywhere we see a fictitious conductivity for X and Y PMLs, we can get rid of that. So for example, in this first update coefficient, we see a sigma Y. That's the fictitious conductivity for the Y-axis PML. That becomes 0, so that this whole term here drops, and this term drops, this term drops, and so on. And what we see is we even have two update coefficients that completely go to 0. And these are ones associated with integration terms down here, so we no longer even need to do these integrations. So that's very cool. And so no more integrations for HX anyway. So we can step through all of these. And here's the final form of our update equation for the HX field. This is with only Z-axis PMLs. So clearly this is a lot simpler, and since we have many more grid points now, it will be very important to do this. If we did a similar thing for the H sub Y, we'd end up here. Our H sub Z looks like this. Notice now we have an integration term. That's because here the field is polarized going into the PML, so it turns out our update equation doesn't simplify quite like the X and Y components did. So we still have an integration term to do here. And remember, we will separate this for an integration term at the top and another integration term at the bottom. It is certainly not incorrect to just do this integration term everywhere. It's just very inefficient now that we have gone to 3 dimensions. So we probably don't want to do that. Our dx, no integration terms. Our dy, there's still no integration terms. And then finally dz, again, here's a field polarized going into the PML. So we have an integration term where we're integrating the curl of the H field, the z component of that curl. Again, this is one we'd want to split into 2 integration terms, one for the top and one for the bottom, rather than integrate it over the entire grid. And then our update equations for the electric field E, these don't change at all. And we sort of knew this. We modularized our code. We pulled off the constitution relation. We kept that separate. And so all of the other stuff wraps into the curl equations, and everything materials related is still applied here in this pretty simple step. Okay, on to our boundary conditions. So you'll discover, again, there's nothing new here, but let's remember all of the spatial derivatives, the x, y, and z's, these are in the curl terms, and this is the only place where finite difference equations reach out to adjacent cells. So this is the only place where we can run into the problem where we have a finite difference equation that needs a value from outside of the grid. So again, we've modularized our code in a way that all of the problems with boundary conditions are isolated to our curl calculations. So let's look at the curl of the electric field. We have x, y, and z components, and anywhere there's a +1 or -1 index, these are the ones reaching to adjacent cells where there could potentially be problems. And what we see is that we only have an I+1, J+1, and K+1. This means for the electric fields, we only have issues at the x high, y high, and z high boundaries, not at the low side boundaries. And it'll turn out when we're calculating curls of magnetic fields, those will only have boundary condition problems at the x low, y low, and z low boundaries. So here's the curl of H. And here our indices are index -1, so an I-1, J-1, K-1. So we have those problems at the x low, y low, and z low boundaries. So we have highlighted where the boundary issues will arise. How do we fix them? Well, here's how we fix it. And again, this shouldn't be any surprise from our previous lectures. So this is the x component of the curl of E. Our top equation is our basic finite difference approximation for the curl. And we do this for the bulk of the grid, except at the x high, y high, and z high boundaries. And each of those is here, of how we handle that, in those bottom 3 equations. So here's the MATLAB code for it. Again, really no surprise, but we're not using if statements. That's the important thing. So I remind you what I like to do. I like to initially set up my loops just going from 1 to nx, 1 to ny, 1 to nz, and I have whatever's in there. So it would start off just being this one equation. I realize, oh, that has a problem at the z high boundary. So I'll make the loop just go to 1 less than the z high boundary. I'll copy and paste this line down here and then handle this explicitly. Then I realize, okay, all of this code has a problem at the y high boundary. So I'll copy and paste all this code out here and handle the y high boundary explicitly. And for the x component of the curl anyway, there is no problems at the x boundaries. That would happen for the y or z components. So the sequence of doing that is routinely how I build my curl calculations. I find I make less mistakes doing it that way. Then for the magnetic field, here's how we fix things. Our first equation is the bulk equation that we do almost everywhere. These last 3 equations are the ones where we do at our boundaries. So at the y low and z low boundaries. The x low boundary isn't here because we're talking about the x component of curl. The y and z components would contain an x low boundary fix. And here's the MATLAB code for it. No surprises. The important thing again, no if statements. Okay, on to our total field scatter field source and how we'll generalize this based on what we know for a fully three-dimensional model. To remind us of our framework, we have our grid scheme on the left, and on the right we're showing we're going to use this total field scatter field framework to inject a one-way source. In this case, that one-way source will emanate from this line all the way across the grid downward toward our device. So it'll be completely throughout this grid downward towards the device, and the plane wave will fill the entire cross-section of our three-dimensional grid. But we'll still define all the points from that total field scattered interface down to be total field quantities, and then above to be scattered field quantities. So the concepts are the same, we just have an extra dimension now. So our correction terms, in one dimensions, we had 2 correction terms, one on each side of the interface. In 2 dimensions, we had correction terms that went all the way across the grid. In 3 dimensions, we have correction terms that go all the way across the grid, but now the cross-section of our grid is 2-dimensional. So we'll have to set up a double loop across x and y to incorporate all the corrections, and then another double loop to incorporate all the corrections on the total field side. So let's think about what those corrections are. So we have, well, let's say we're on the scattered field side, we're calculating the curl of E, it reaches to the total field side, so we have problems. Here's the x, y, and z components of the curl of E. Here's a term that's reaching to the other side of the interface, so we have problems with the x component of curl. Here's another term that reaches to the total field side of the interface, so the y component of curl has problems. But notice the z component of curl only uses x and y components of E, only x and y derivatives, and so this does not reach to the other side of the interface. So there is no corrections to the z component of curl. We'll only be incorporating corrections to the x and y components of curl, and only these 2 terms. So these 2 terms are total field quantities. We'll end up subtracting the source from it to make them look like scattered field quantities. So we do that, we subtract the source, we bring it to the outside of our expression, and what we end up with is our original curl equations, which tells us, just like before, we can set up our double loop, we can calculate curl without knowing anything about total field scatter field, and then when that is done, we'll set up another double loop to go over this range of values right at the interface to add and subtract these 2 correction terms. So we're adding a correction term to the x component of curl, and we're subtracting a correction from the y component of curl. And so here's how we would do that. 2 simple lines of code in MATLAB. Now we have curl terms on the total field side, and these contain terms from the scattered field side when it reaches across. Again, there's no corrections to the z component because we only have x and y derivatives. They're not reaching in the z direction. So it's the x and y components that have problems. I've highlighted in red the terms that have problems. It's a k minus 1. They're the ones reaching to the other side of the interface to be scattered field quantities. We want those quantities to look like total field quantities, so we'll be adding source terms to those to make these scattered field quantities look like total field quantities. When we do that, just like before, we get our original curl equations back. This means we can set up our triple loop over x, y, and z, calculate the curl everywhere without considering anything about total field scatter field, and then when we're done, we set up a double loop over this plane to add and subtract these correction terms. Okay, so now we need our correction terms. Notice now we actually require 4 different things. We need the x and y components of the electric field source, but from the total field side, and the x and y components of the magnetic component of the source on the scattered field side. So we actually need 4 functions now. Before we just needed 2, the e and h components. Now we need 2 e's and 2 h's. So we'll start with the electric field, and in general the electric field is some polarization vector times a cosine. And we have our frequency minus k naught nz. So this is talking about a plane wave traveling in the positive z direction, being injected in a region with refractive index in ints. The other thing that we want to do that's always good practice, this polarization vector can point in any direction, but we want to make its magnitude 1. And we always give this a unit amplitude source. So if we separate this into x and y components, this is what we get. Now, the x and y components of the electric field are at physically different positions. However, since we're talking about a wave at normal incidence, there's no phase difference between them. So nothing really needed to happen here. And there is no z component, so we don't even really have to worry about the z component of that polarization vector. That it should be 0 because we're talking about a TEM plane wave. But the magnetic field component's a little bit different, and we calculate that from Maxwell's equations, where we'll put in our expression for E and we'll get out an expression for H. And when we work through that, here's where we end up. So notice the X component of the magnetic field gets information from the Y component of the electric field. Likewise, the Y component of the magnetic field gets some information from the X component of the electric field. So notice that crosses here. One term has a negative, the other one has a positive. Keep that in mind. Certainly the square root of epsilon over mu, that comes from the impedance of the material, and otherwise this cosine term has not changed. So what we've shown through Maxwell's equations is that we have now expressions for the amplitudes of the H. We need now to consider the time delay and the cell differences on either side of the interface. So here's how we can calculate that. We'll calculate the electric field just as an ordinary Gaussian, nothing magical here. For the magnetic field, we realize they have different amplitudes due to the impedance. We also notice that the x and y terms are sort of crossed. Don't forget that. And then we have our Gaussian function with this delay. And we have 2 time cells difference and a half time step difference. So that's how we calculate our delta t. So now we have a Gaussian source. Gaussian plane wave source. So if we're looking at a 3-dimensional finite difference time domain model using this slice command, notice I'll take a slice through the middle of the field array and visualize it. And here's another slice that we're seeing mostly in this view. And then also a slice through the middle. We can see our pulse source, if you will, but in 3 dimensions now. So this is a pretty typical view of what you would see in MATLAB running a 3-dimensional finite difference time domain code. Now we need to generalize how we calculate transmittance and reflectance. There's more directions now for our diffraction orders to diffract into. So let's draw a block diagram of how we're calculating things. You'll notice this is not a whole lot different than what we've talked about before. But we run our model and we calculate the steady state components of EX and EY on both the transmitted and reflected side. Now, at that point, the simulation's done. So what's in green here is really the FDTD simulation. The rest of this is post-processing. So the first step in that is to calculate the transverse wave vector expansion. So that's the X and Y components of our wave vectors. Then we set up a loop over frequency. And for each frequency, we'll calculate the longitudinal components of the wave vectors. Then we interpolate all of the fields that we calculate up here at the origin. We normalize to the source frequency. Then we calculate the amplitudes of the spatial harmonics. This will be through a two-dimensional FFT now. But we only know the X and Y components of those. So we'll calculate the Z component of the amplitudes of the spatial harmonics. Given that, we have all the information to calculate the diffraction efficiencies of our spatial harmonics. Then we can add up all the reflected ones to get overall reflectance. We can add up all the transmitted ones to get the overall transmittance. And we do that for every single frequency. So let's visualize these calculations now. So during a simulation, for each frequency we're interested, I'm only showing one frequency. We'll be calculating the steady state fields in this reflection record plane. And so we have an X and a Y component that we need. Likewise, down here, we'll be Fourier transforming to calculate a steady state field in the transmission record plane, and we need the X and Y components again. We're not Fourier transforming the magnetic fields. We only need the X and Y components of the electric fields. But we have two of these going now, X and Y components. So if we have a cross-grading device, which I'm showing here, something that's periodic in X and Y, and if we look at our reflected diffraction orders and transmitted diffraction orders, they look something like this. They're heading off all in different directions. And so we need to calculate diffraction efficiencies associated with each one of those. Well, at first, our transverse wave vector expansion is this. And since we only have normal incidence, these terms here, kx ints and ky ints, will always be 0 in finite difference time domain. And so we really only have these terms left in our expansions. That's why we can calculate these without knowing frequency. So they'll be independent of frequency. Then we can calculate, or we can construct, if we wanted to, the transverse component wave vector. We don't explicitly need this, though. So M and N are arrays that, for example, if our grid's 11 points across, capital M will go from -5 to +5, passing through 0 to give us 11 points. So we do this in two directions now. So we have M and N. Then we calculate our expansions, Kx and Ky. Then we do a mesh grid, because we're actually diffracting into an array of plane waves. A two-dimensional array of plane waves, if you will. Another visualization after our mesh grid, our KX mesh grid looks something like this. Notice there's redundant information here. Our KY grid looks like this. Notice there's redundant information here. But really, when we look at these together, and we look at the transverse component of our wave vector, there's not really any redundant information. We really need both sets here. So these are what the transverse components of our diffraction orders look like. And we would need to phase match every single one of these into whatever region we're interested in, the reflection region or transmission region. So how do we phase match? Well, we use the dispersion relation to calculate the Z component. And so we have the square root of the magnitude of our vector minus the transverse component of the wave vector squared. And so now we have the difference between two things. We could have something that's real or imaginary. Again, something that's real or imaginary If these longitudinal components are purely real, that's a propagating plane wave. That's one we want to count as reflected or transmitted power. If it's purely imaginary, that means it's evanescent and we want to ignore it. So once we calculate these things, what we'll see if we looked at just the longitudinal components is that only the lowest order few usually are real and propagating. The rest are evanescent. In fact, most will always be evanescent. And so we ignore these because evanescent fields don't contribute to power flow, except for that tunneling situation that I mentioned in a previous lecture. But these we need to account for. That is what will transport power into and out of our device. So here's more visualizations of this. Again, here's our transverse wave vector expansion. If we look at these on the reflected sides, here's what the longitudinal components look like. If we put these two together, here's what everything looks like on the reflected side. Most of these are evanescent, but we do have some that are certainly propagating plane waves all at different angles. And on the transmitted side, most are evanescent, but we still see a whole bunch here that are carrying power away from our grating downward. Now notice there's a whole bunch more on the transmitted side than the reflected side. Clearly, in this case, that's because the refractive index on the transmitted side was higher. If it was higher on the reflected side, we would see more modes than on the transmitted side. We need to interpolate our field components. We've just calculated X and Y components. We really want to bring those together to describe a single vector quantity, but we can't when they're at physically different locations. So the best thing to do, I think, is to interpolate all the electric field components to exist at the origin. So if we look at our X component, to interpolate at the origin, we need to average this with the electric field from the previous cell. So notice that's what we're doing. We're averaging the field in the same cell with the field in the previous cell, and it's just an average. And we do this for both X and Y in both the reflected and the transmitted regions. And so, pretty simple MATLAB code to do that. Now we've interpolated all the electric field components at the origin, and now we're ready to move on. We can assemble that vector quantity. This is a good point to normalize to the source. Remember, the source spectrum rolls off with frequency. That will artificially make our reflection and transmissions roll off with frequency. That's not a real thing. So we divide by the source, and that makes it look like the source has unit amplitude for all frequencies. Now we want to calculate the amplitudes of the spatial harmonics. So we calculate the X components of the electric fields. We do a two-dimensional FFT on those, and we calculate the X component amplitude, and so on. If we have the Y component of the electric field on the reflected side, we calculate the Y component on the reflected side of the amplitudes of the spatial harmonics. We do this on the reflection side and the transmitted side. Notice we're still missing the Z component. We need that because we're not really confident of the overall magnitude of the spatial harmonics yet. So we need the Z components. So how do we do that? Let's go back to the divergence equation. Remember, originally it was del dot D equals 0. We replaced D with our constitutive relation, so it's del dot epsilon times E equals 0. Well, epsilon in the region where we're calculating these anyway is constant, so it can come to the outside of the del operator. We divide both sides, and we just end up with del dot E equals 0. We replace E, because we're talking about one of our spatial harmonics, with S and the exponentials here. So in terms of E being a spatial harmonic, here's how we express it. It's magnitude or amplitude, and its propagation terms. So then we expand this divergence operation. We have the derivative of the X component, Y derivative of the Y component, and the Z derivative of the Z component. And when we do that, we end up with this equation. The exponentials ended up all dividing out after we took the derivative operations. Then we solve this for S sub Z, and now we have an equation for the Z component of our spatial harmonics in terms of the X and Y components and our wave vectors. So we use this equation now to calculate the z components of our spatial harmonics. So 2 lines of MATLAB code. Once we know the x and y components from our 2-dimensional FFTs, then we calculate our z components. Now we know everything about the amplitudes of the spatial harmonics. So we're ready to calculate diffraction efficiencies. So here's the equation. We calculate our diffraction efficiencies. Just to remind you, this term, which is squared, we used to be dividing by the amplitude of the source squared. However, when we normalized it to our source Fourier transform, we essentially made it look like our source had a unit amplitude. So we are dividing, but we're just dividing by 1, so we don't even bother to write it here. But we'll come away with diffraction efficiencies on both the reflected and transmitted sides. So here are the overall amplitudes of our spatial harmonics, and that's what we use in these equations down here. This really is the amplitude squared, and I'm probably not conveying that here. But so these are our amplitude squared. And so now we know the diffraction efficiencies on the reflected and transmitted sides. Then we add them up. If we add up all of the diffraction efficiencies for the reflected diffraction orders, we get overall reflectance. And we add up all the diffraction efficiencies of the transmitted diffraction orders, we get overall transmittance. So that's real simple to do in MATLAB. And then a real good thing to do is to add the reflectance to transmittance and make sure we get 100%. Even if we intend our model to include loss or gain, we would turn that off initially. We really wouldn't get an accurate simulation, but we can check for 100% conservation, because if that is not 100%, then we haven't iterated long enough, or there's some other kind of error in our code. And so we can fix that. Then when we turn the loss and gain on, the fact of having loss or gain won't hide some potential error in our code. Okay, last thing I want to share with you is this slice command, because it's the easiest. It's not the only way, and maybe not even the best, but it is certainly a very easy way to visualize three-dimensional data in MATLAB. So it's called slice, and we will create a three-dimensional mesh grid, X, Y, and Z, and we'll give it V. That is our three-dimensional set of data. So if we're visualizing the Z component of the electric field, for example, that's what we'll give it, our three-dimensional E sub Z. Then we give it lists of where we want to place our slices. So SX is a one-dimensional array of positions to place slices that are perpendicular to the x-axis. And likewise, SY is a 1D array of all the different positions of planes that we're going to place distributed along the y-axis that are perpendicular to it. And then the same thing for S sub Z. So we could do any number of slices. The more slices you get, though, it gets a little bit confusing to look at, because the slices hide the other slices, and you end up having to orbit around your graph to see things. So I tend, for most of my simulations, just like to slice through the middle of each axis. So I'll just set these to usually zeros. If my axis goes from a negative number to a positive number, I would just set these to zeros. If your axes are going from 0 up to some positive number, then you'd want to set these at the midpoint, just a single number for each. I think that looks best. There certainly are circumstances that you want to probe the field in other planes, and you'd stick in other values at that point. But a good place to start is just a single value in each one to be the midpoints. So what does it look like if you do this? Here's a good example of how I do it. And this is also taking into account our rotated grid. So we give it Y, X, and Z mesh gridded. I put a negative in here, and that just flips it. There's other ways of doing that. I'm being lazy here. We can actually go into the properties of the graph and flip it or whatever. I'm visualizing the X component of the electric field, and I give it 0, 0, 0. And that's how we cut these slices through the middle of each axis. And then I'll always go axis equal tight off. I'll give it a color bar so we know what amplitude. We're talking about a unit amplitude, so that's clearly our source we're looking at. And then we give it some view, some three-dimensional view. So this is azimuth and elevation. Azimuth is sort of the radial angle. Think of like a tank, and as it turns, it's changing that azimuthal angle. And then the elevation angle is sort of the height of the gun, if you will. So we're looking slightly down on this at about 20 degrees, and then rotate it around from looking straight on it to about 75 degrees. So you can play around with those. You can also orbit around it yourself. And at the lower left of the figure window, you'll see the azimuth and elevation that you're currently orbited to. And so you get a view you like, remember those numbers, and type it into your code, and it'll always come up in that orientation.